All right, we've talked about matrix multiplication. We know that matrix is like a table of numbers. In this section, we're going to talk about breaking that table up into subtables, and this is called block matrices. Now, here is a breaking up of the matrix, or what we could call a partition of the matrix into 4 parts. We drew this line here to divide the top and the bottom. We drew this line to divide the left from the right. So here we have a 3 by 3, a 3 by 1, 1 by 3, and 1 by 1. The 3 by 3 is called A, 3 by 1 is called B, 1 by 3 is called C, 1 by 1 is called D. All right? So the blocks must fit together. So in other words, the number of columns of C should be equal to the number of columns of A. The number of rows of A should be equal to the number of rows of B, etc. All right? So the sizes of the subblocks have to be compatible. Now, of course, there's more than one way of dividing a matrix up into blocks. But it turns out that once you've divided the matrix up into compatible blocks, you can multiply matrices block by block. So the block in the upper left-hand corner of the product of these 2 block matrices can be written this way. And if you work this out, this is the same number you'd get as if A, B, and C, D were numbers. Okay, so you basically can divide a matrix up and treat the parts of the matrix as numbers themselves. Now, these matrix products, they do associate, but they don't commute. But still, you can compute these results block by block. Okay, and here's a practical outworking of this example in the of these equations in the example that's given above. All right, you can work it out that, in fact, with the blocks up here, you do get that result when you multiply m by itself. All right? So that was a short section. Let's go on to square matrices. Okay. If we have square matrices, if we want to multiply square matrices together, then they have to be exactly the same size. Because as we saw before, the number of columns in the first matrix must be equal to the number of rows in the second matrix. Now we can take powers of square matrices because we can multiply them together arbitrarily. So for instance, m cubed is m times m times m. And we define m to the 0 as the identity matrix. That's just our definition. Since we can take powers of square matrices, we can actually define a polynomial of a matrix. So here we have this polynomial f of x equals x minus 2x squared plus 3x cubed. And here we have a matrix M. In fact, we can take f of m by plugging m in to these places here. Just compute m here, m squared here, m cubed here, and you take the polynomial, that gives us the result. Right here, we computed m squared, m cubed, plugged it in to f, and got f of m. Now, you can in fact do the same thing for a Taylor series, which is just a big long polynomial, infinite polynomial. So I can have a Taylor series of a matrix. Now, there is a Taylor series of the exponential function. The exponential function has this Taylor series, 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. You learn that from calculus. Now, we can do the same thing for a matrix. All right, we can have I plus m squared plus m cubed. Now, I is the same as 1 because they both function as the multiplicative identity. Right. Now, we can actually do something with this. If we have this matrix exponential expressed as a power series, we can multiply these power series together and get a result. So, for instance, I get this result, xbem times xbem equals x2m, by plugging in the power series for m here, power series for exponential of m here, and I can get out the power series for the exponential of 2m here. I know this is true, e to the x times e to the x is e to the 2x. It turns out that it's also true for matrices just by plugging in power series, and it works the same way. Okay, that's it for this video.